Alright, welcome to the second video. In this video, we shall discuss all the problems that came in 2019 in the geometry section. The first problem turns out to be a rather straightforward problem, but it will also provide a great opportunity to revise very important formula, which may not be required in this particular problem. So we're talking about an equilateral triangle, and we are interested in the circum radius, which means we are looking for the perpendicular bisectors of each of the sides. Now, this point turns out to be the center of the circumcircle, but since this line also turns out to be the angle bisector, and in fact also the median, this will also be the center. The point O will also be the center of the incircle. Now, from this diagram, we can see that this is the circum radius, and then the perpendicular drawn from that point is going to be, this distance is therefore going to be the in radius. And finally, since AD is also the median, and this point O is also the centroid, we have the famous relationship, which is AG by GD is 2 upon 1, and this implies in this particular problem R by R is equal to 2, which is clearly a constant. And this means that this is a very easy problem. However, let's take the opportunity to also write down two extremely important formula regarding the circum radius, which is 4r is equal to ABC, where ABC are the sides of the triangle, divided by the area of the triangle. So this is a nice formula which is not required in this simple problem. And there's another formula associated with the in radius, which is RS is equal to the area of the triangle ABC. Now, I would like to take a few more minutes and show you that these two problems are particularly easy to derive and also very symmetric and nice looking. So let's do it right away. Let me do the circum radius first. So we just have to use the standard convention, which is write down the sides ABC and the angles. Now, the first formula follows very easily from the favorite sine rule, which is definitely extremely elegant and symmetrical looking and can be easily derived. And this straight away gives us the first formula. For example, we can write the area of the triangle as half AB sine C and quickly substitute for sine C as C by 2R, and we are done. 4R is equal to ABC over the area of ABC. So this was too easy. Now let's get to the next formula, which is that for the in radius. For that, we just have to draw a very nice picture right here, and that goes like this. So this is, let's say that this is the in radius, and what this means is if you draw a perpendicular from the in radius to the three sides, they'll all be equal. And now here's a simple construction. Just construct three triangles like this. So let's call them this whole triangle. This whole triangle, let me call it as 1. And this triangle is 2. And this triangle is 3. And don't forget that these are perpendiculars drawn to the sides. And that would mean that the total area of the triangle is the area of triangle 1 plus the area of triangle 2 plus the area of triangle 3. And this is simply half C into R plus half A into R plus half B into R, and this is equal to half A plus B plus C into the in radius, and this is written as the semi-perimeter into R. So the area is simply S into R, and we have again derived the formula rather easily. Just to repeat, S is the semi-perimeter, half of A plus B plus C. Alright, so now let's look at the second problem, which also affords a great opportunity to look at some standard but nice formulae. But first of all, I would like to point out that there's a small tricky part in the beginning, which will be easy to handle if we make a good job of drawing the diagram. So here we go. Now this is a very popular configuration. We have this particular angle as 90, and then there's lots of other information that is given, which is that there is an altitude which is AD, and this is 90. Now some more information is given, which is that there are two more lines drawn which make an angle of 90. So this is the trick part, I think. So we have DE and also DF. The trick part here, okay, what is he asking? He's asking for EF, and it's important to upfront realize that A, E, D, F is a rectangle. So that's, I think, is the tricky part. And once we realize this, we immediately know that EF is nothing but AD. And the question really is, what is AD equal to? And all of a sudden, this becomes a well-known standard problem. So the question is, what is the length of this blue line? Let's call it H. So AD is equal to H equal to what? Now, here are the information given. Here A is given as 25, the hypotenuse, and C in this case has been given as 15, and this immediately tells us that B is equal to 20 by the Pythagoras theorem. Now, what are the standard formulae that we have been referring to, which is if this side, if we just call it as A1, and the other side we call this as A2, then H square is equal to A1 into A2. Now there are formulae which also say that A into A1, please refer to the diagram here, A into A1 is equal to C square, and also A symmetrically A into A2 is equal to B square. So these are well-known formulae in this configuration, and this information needs to be put in here, and that's the end of the problem. So let's get done with the calculation. This implies that H square is equal to C square over A multiplied by B square over A, and H is equal to B into C by A. And now we just need to substitute the numbers. 20 into 15 by 25, and this is nothing but 12. So straightforward formulae, important formulae, and that's the end of this problem. Okay, now let's look at the third problem, which turns out to be more of an algebraic manipulation, but it does use one of the most important formula. So let's draw a good diagram as always. Now this is standard notation, and we denote the sides and the angles with the standard notation. And in this problem you can see that it is given that C square is equal to 2AB and a square plus c square is 3b square. So part of the manipulation is fairly reasonable. We substitute for c square and then complete the square. I'm sorry, this was a mistake. And complete the square. So we get a plus b is equal to 2b, and therefore a is equal to b. So this is really an isosceles triangle. And now for the angle, which is the question, we shall use the cosine rule, which is c square plus b square minus a square divided by 2bc. Now a is equal to b, so this goes away, and this is equal to c over 2b, and this is equal to root of 2ab, and I'm just going to write it as a square divided by 2a, because a is equal to b, and this turns out to be 1 by root 2, and therefore this implies that a is equal to 45 degrees, or pi by 4. Now cosine rule is going to be an oft-repeated theme in many of the algebraic calculations and geometric problems, and I'm sure we'll have repeated opportunities to return to this particular formula. Alright, the next problem is also very interesting and easy if you have seen some of the standard properties that we're going to use in this problem. Let me just first solve the problem up front, and then we'll discuss the properties I'm referring to. So we have a convex quadrilateral, which we shall call A, B, C, D, and there are midpoints K, L, I think I should use another color, K, L, M, and N are the midpoints of this convex quadrilateral, and it is given that P is some interior point, so P could be anywhere, so let's call this as P. And given that P is some interior point, the area of PKAN, so we're talking about this particular triangle, quadrilateral, and this area that has been marked here has been given as 25. This area is 25. Now what's the next one? PLKB. So we're talking about this area. It has been given as 36. And PMND, so we're talking about this area now, has been given as 41. So this area is 41. And finally, the last quadrilateral, PLMC, which is this area, is equal to what? That's the question. Now, let me tell you the answer up front, and we'll justify it by standard theorems. The answer is that the yellow areas is equal to the blue area. And those of you who see this easily will of course get the answer rather quickly. And so assuming that the yellow areas is equal to the blue areas, and let's call this as X. So 25 plus x is equal to 36 plus 41, and this implies that x is equal to, how much is it, 41 plus 11, that is equal to 52, and we are done. So how does one realize that the yellow areas is equal to the blue areas? So let's look at the standard results. We don't need to refer to the problem anymore, so I shall now discuss why is it so. So first, let's look at what happens when, this is something that you must have surely met, when you join the midpoints like this and midpoints like this. These two lines that I've just drawn will definitely be parallel to the diagonal AC, and this area, so the area of the shaded portion here, KL, so area of KBL is definitely going to be 1/4 of the area of the triangle ABC, because of similar triangles and the ratios being half. And similarly, the areas of KLMN, so the area of DMN is going to be 1/4 the area of ADC, and this implies that the sum of the areas that I've shown here, so I'll just write it like this, is going to be the sum of the LHS areas is definitely going to be 1/4 of the area of the quadrilateral ABCD. So this is one observation. Now, what about the other theorem that I'm referring to? So I shall now erase this, and let's look at any parallelogram. Okay, so this is the other theorem that, if you're well versed with, you will agree with what was stated about the problem. Take any parallelogram A, B, C, D. Take any point in the interior, point P, and then join this. Then these two triangles, area of these two triangles, let's call them 1 and 2. So I'm just going to write here 1 plus 2 is definitely going to be half of the area of the parallelogram ABCD. And why is that? Because the area of 1 is going to be half AB into, okay, so since these two lines are parallel, they have a common perpendicular. So if we call this as H1, then this will be H2. So half AB into H1. And similarly, the area of 2 is going to be equal to half DC into H2. And this is nothing but half of AB into H1 plus H2, which is equal to the area of the parallelogram ABCD. And that means that 1 plus 2 is definitely going to be half of the area of the parallelogram for any point P in the interior. So these two standard results lead to an easy solution of the problem, right? So the next problem does look very lengthy, but once again, it turns out to be fairly straightforward once you begin to understand what is being asked and what is being given. So the first thing is that the perimeter is fixed for both the circle and the triangle. Now one quickly realizes that if the perimeter, which is equal to 2 pi r, is fixed, then this implies that radius is fixed, which is equal to L upon 2 pi, and this implies that the area of the circle, which is equal to pi r square, and since r is fixed, the area is fixed. So there is no issue with the numerator. The numerator is a fixed quantity, constant. Now let's look at the triangle. If you fix the perimeter of the triangle and let's say that L, and we take a isosceles triangle, maybe slightly less than L by 2, so L by 2 or nearly L by 2, and bring them very close to each other. So this can be epsilon. One can imagine that the perimeter is equal to, nearly equal to L, but you can see here that the area is half epsilon into height, which is nearly L by 2. So this is small. So by taking epsilon extremely small, you can make the area of the triangle very small. And that means that the ratio, this ratio can always be made as big as we wish by reducing the area of the triangle. And this is precisely what is the content of the statement, that the ratio can be made greater than any number that we wish. And in this case, A is the alternative. Using the same logic as given here, you can rule out that all of them B, C, D are not right. The last problem actually turns out to be fairly tedious algebra, and much will be facilitated by drawing a neat diagram and labeling it properly. So this will definitely require some amount of practice. But there is more tedium to this problem. You are supposed to know the sines and cosines of angles such as these, which is also pretty standard though. Anyway, let's get on with the algebra. So there is A, B, C, and it's an isosceles triangle. So AB equal to BC, and therefore this perpendicular will be a bisector, and we shall attempt to find the angle which is half of the required angle in the problem by finding out the value of the sine of this angle. So let's call this as x, and the two equal sides as A. Now there's some algebraic information that is given, that there is a point x such that this distance AX is equal to AC, which is 2x, and that means that AX is 2x. So with this sort of labeling, the calculation now proceeds pretty smoothly. So it's given that AX over XB is equal to AB over AX, and now we just substitute all the labels we have taken, and you will end up with a quadratic. this gives us 4x square plus 2ax minus a square equal to 0. Now we shall proceed to take the positive root of this equation, and therefore we'll have to take a plus sign here instead of the minus sign, and just use the quadratic formula. Right, so the value of x turns out to be equal to a into 1 plus, minus 1 plus root 5 by 4, and all of this implies that sine of this angle, so sine of half of the required angle ABC is equal to x by a, and that is equal to root 5 minus 1 by 4. And you're supposed to know that this implies that half of ABC is equal to 18 degrees, and that means that the angle ABC as required in this question is 36 degrees. So the only way to get this algebra right is by lots of practice, but it should not count as a very tough problem.